Okay, yes, let's talk about stellar spin. Let's talk about exoplanet dynamics. So as we all know, stars are born with spin. In this case, I'm showing a plot for sun-like stars. They're born with quite a wide range of spin, but as they age, their magnetic fields interact with their wind, and they lose that angular momentum of that spin to their wind, starting at about 100 megayear, and after a gigayear, this wide diversity of spin is gone, and sun-like stars are spinning at about the same rate. This is really great for gyrochronology. It's not so great if we would want to know the initial spins of stars. It's sort of lost information. And additionally, stars are not rigid bodies. They are squishy, which means when they spin, that makes them oblate. They bulge around their equator, and this changes their gravitational potential. And what this is going to do, it's going to cause precessions in the orbits of the planets, and those precessions are parameterized by the stellar oblateness, a number J2. Yeah, and J2 can have a pretty significant effect on the orbits of planets. Here, I'm just showing some sample evolutions. On the top curve is a 90th percentile initial spin sun-like star, its spin evolution over time, and on the bottom curve is a 50th percentile in spin. So J2 is really good at misaligning ultra-short period planets from their companions, hot Jupiters, and combined with stellar obliquity, which Milena talked to us about earlier, it can completely destabilize systems. It can just rip them apart, cast the planets onto each other, and be quite dangerous. So okay, let's put a pin in that. J2, precessions, evolves with time. And let's talk about planet-planet dynamics. So planets, of course, have mass. They interact with each other through their gravitational fields. And to second order, what this does is cause precessions in the orbits. And so here, what I'm showing you for a fiducial three-planet system is the precession frequency of the longitude of the pericenter, written with var pi, my favorite not Greek letter. And in the black lines are the precession frequencies of the outer two planets, and in the dotted blue line, the precession frequency of the inner planet. And we can see, as a function of the inner planet's semi-major axis, the inner planet can have the same precession frequency as one of its companions, depending on where it is. And what happens when two things precess at the same rate? You get a resonance. So if we calculate to second order how much eccentricity we expect gravitational interactions between the planets to excite on the inner planet as a function of semi-major axis, you get a curve that looks like this. So where there are intersections, where there are resonances, you're going to have the outer planets extract angular momentum from the inner planet and increase its eccentricity. Now, okay, this is a nice tail, but the range of semi-major axes where these resonances occur is pretty small. Like that one on the left, quite thin. If we plot here in terms of parameter space in semi-major axis ratio, so on the bottom, we have middle planet to inner planet semi-major axis ratio. On the y-axis, outer to inner. And then on the color, we have the inclination, sort of the maximum inclination relative to its companions that the inner planet gets because of these mutual gravitational interactions. You can see there's structure here. There's this big strip that runs up the middle, and that corresponds to a resonance. And now, as I said before, this strip is pretty thin. We would expect, naively, that these resonances to be pretty rare. However, I'd like you to extract that pin. I told you to put in J2. I said that J2 causes time-varying precessions. These resonances occur when two things precess at the same rate. So perhaps if J2 is causing these time-varying precessions, it can boost a non-resonant system onto a resonance and maybe expand the resonant region of this parameter space. Okay, and so on the left, we have that plot I showed you 2 slides ago. That corresponds to J2 equals 0, a non-rotating star. And now on the right, for inclination on the top and eccentricity on the bottom, let's see how when we start with a fast-spinning star that spins down, how that changes things. So let's hope this movie plays. Okay, great. As the star spins down, the resonance forms into one big peak and then splits and slides all across the parameter space. That oscillation you see in the top and the bottom, let's play that movie again. That oscillation is just aliasing, it's not physical. So we expect if we include the evolution of the stellar spin for these resonances to occur in a wider range of systems. Putting that back into a familiar form, now we can see that this resonance moves across this parameter space, and if we sort of smear out all times, all J2s onto one plot, now instead of one tiny resonant strip, we have a big resonant triangle. Okay, so now that we're including stellar spin, we do expect the resonances to occur more often. Let's do a concrete example. My second favorite planetary system, Kepler-9. It exists in a regime where if its star is born spinning fast enough, it should hit one of these resonances. And what do these resonances do to the orbital elements? So what it's going to do is it's going to misalign the inner planet from its outer companions. Kepler-9 is a 3-planet system, and the outer 2 planets are going to align. So in green, we can see the mutual inclination between the inner planet and the middle, and in blue, hidden behind the green, between the middle planet and the outer. And you can see that the inner planet gets misaligned and the outer 2 planets align. All right, so that's great. You also get some eccentricity excitation also. How common is this in the observed exoplanet sample? So I constructed a clean sample of 33 planet, all transiting systems orbiting stars below the Kraft break, and I found that 6 of them exist in regimes where if their stars were born spinning fast enough, then you would expect these resonances to occur. So 6 out of 30, that's 20%. I would say that's pretty common, more common than Friday, which is today. My apologies if you've heard that joke multiple times from me giving this talk to you. Okay. All right. So you have these resonances. They occur in some fraction of systems. Let's talk about transit probabilities. So while I put this figure up, let me tell you a story I'm going to tell. So I told you that when the resonance occurs, the outer 2 planets align and the inner planet gets misaligned. What this is going to do is obviously going to increase the probability that the outer planets transit together when the star is viewed from a random angle, and it's going to reduce the probability that the inner planet transits with them. And now the story goes that the inner planet is orbiting so close to the host star that even though it's getting misaligned from its outer companions, that's not going to be as big of an effect as the alignment of the outer 2 planets increases the probability that all 3 planets are observed transiting together. So Kepler-9, which is labeled here, and Kepler-619, another system I'm going to be showing you a lot of plots of on the next slide, are both these 3-planet systems where we observe all 3 planets transiting. And so the story goes that if the star is born spinning fast, if the resonance can occur, then we expect there to be a higher probability that all 3 planets transit, as we do see. And you can just do this calculation. So here are the results of a Monte Carlo, where I assumed an initial, a Rayleigh distribution of initial inclinations for the planets, I think with a sigma of 0.06 radians. So on the x-axis here, we have the initial J2. That's a proxy for the initial spin of the star. High spin on the right, low spin on the left. And on the y-axis, the probability that all 3 planets transit together. And you can see that at about 8 times 10 to the minus 5 initial J2, there's a bump. So the probability that all 3 planets transit together, as observed, increases from just above 3% to just under 4%. A modest growth. It's about a 25% increase in your percentage points. Representing this same data in a different way, you can now on the x-axis, we have the initial mutual inclination between the outer 2 planets, same probability on the y, and now the color bar is the initial J2, and you can see very clearly that for almost all initial mutual inclinations for the outer planets, the high J2, the higher spin stars transit more often, which is more consistent with what we see. And just to confirm, here I'm showing you a very similar plot, but now it's the probability that the outer 2 planets transit together, irrespective of what the inner one does. The outer 2 planets are aligning. Of course, at high J2, they're going to transit more often. Okay, and this is the story. The story goes, high J2 aligning the outer planets, the inner planets misalignment doesn't matter that much. Transit probabilities increased all around. And that story is compelling, it's nice, it's even true, but it's not the whole truth. So what I'm showing you here is for Kepler 619, the probability, 3 different curves for when viewed from a random angle. You see exactly 1 planet transiting, exactly 2 planets transiting, and exactly 3 planets transiting. And we can see that boost in the 3 planets if we squint. From before, you can see a boost for the 1 planet case, because of course you're misaligning the inner planet from its companions. It's going to transit alone more often. But the probability that exactly 2 planets transit, which used to be much greater at low J2 than all 3, plummets. It plummets by almost half. And what this means is that what this resonance is doing is it's bifurcating the system. You're splitting off the inner planet, you're aligning the outer 2 planets, and so you miss all of these opportunities to see the inner planet and the middle, but not the outer, or the inner planet and the outer, but not the middle. If we produce the same plot for Kepler-9, it's a very similar story. There is, in fact, again, if you squint, an increase in the probability that all 3 planets are observed transiting in Kepler-9, as we do observe, another increase in the 1 planet transit case, but a decrease in 2 planets. And if you add the orange and the green curves, you get the probability that at least 2 planets transit. That goes down by about 1/3. In other words, these resonances, while they're beneficial for high multiplicity transits, the probability of 3 planets transiting goes up. Overall, if you want to see 2 or more planets, that probability goes down. So a land of contrasts. I'll put up my summary slide, and I'm happy to take questions.
Hi, Thea, great talk. Did you say that this has a time varying effect? So is it possible to imagine that planets could kind of come in and out of our transit window as time goes on?
Yes. So the J2 of the star is always going to cause these precessions. The mutual inclinations between the planets are always going to oscillate. What I've been showing you are mean probabilities, so like integrated over a long time. Yeah, it is possible that in a scenario where you're unlikely to see 3 planets, you do, or where you're likely to see planets, you don't. Everything does time vary. What I'm showing you are averages.
Oh, okay. Do you know on what time scale that might vary?
It'll be on the dynamical, like the secular time scale for these systems, which will be like 10,000 years.
Oh, okay.
At least 100 years.
Got it. So like not really detectable.
Not really detectable.
Gotcha. Thank
Unless the star is presently spinning very, very fast. There's Alexander Stefan wrote a paper about that.
How fast is fast?
I would say 1 day is fast.
Is that online?
Yeah.
What's the one first?
Hey, Travis Metcalf, nice work. At least in models, the prediction is that initially fast rotating stars compared to initially slowly rotating stars are expected to have a different degree of differential rotation. I wonder if you've looked for any evidence of that.
Like evidence for that within the observed planet sample? I have not looked for that. That's a great idea.
From online, what role does tidal dissipation inside the innermost planet have on the resonance?
Yeah, so the misalignment and the pumping of eccentricity happens much faster than the tidal timescale, even when you're quite close, as these planets are. The eccentricity is going to get tidally circularized away long before we can observe it, though the inclination should remain if unless we have like a hot Jupiter and what JJ talked to us about yesterday happens, and then you realign everything. But the inclination should stay constant for small planets.
All right. One last really quick question.